I have no idea what just happened there, but I might have made everything messed up. But anyways, I went to hit my window to bring it up to the front, and I hit the one place that happened to be treated as a recording. So it just stopped recording. So yay for that. But anyways, looks like I'm recording now. Anyway, so we are starting chapter 7, which is on work and energy, and this is a whole new way of doing it. The problem with the way we were doing it is we were using Newton's second law of motion. Of course, we were using Newton's first law and Newton's third law as well, but Newton's second law, the summation of forces is equal mass times acceleration, is really a vector equation. So everything we pretty much had to do was related to vectors and use vectors, but it would be really nice if we can do some things. Maybe we have to be limited on exactly what we can do, but if we can still do a lot and not have to use vectors, that'd be nice. Well, that method turns out to be something called conservation of energy. So if we use conservation of energy, that gives us another way of doing it. And in fact, you can pretty much get the same answers to stuff you did. But what it turns out to be is I've sort of recognized this conservation of difficulty. So for instance, if you find a really easy way to do, let's say, find out the acceleration by using F equals ma with vectors, then what you might find out that is that A, if it's really easy in the vector way, when you go to the scalar way, you might find A is really hard, but other things that were really difficult in the vector way are actually easy. So for instance, finding the final velocity is a little bit more complicated in the vector world because you have to find the initial velocity vector, you have to find the acceleration, then you had to multiply the acceleration times the time, then you have to take that vector quantity, add it to another vector. So that was kind of a complicated thing to get when we were doing it vectorially. But now it turns out if you use conservation of energy, that turns out to be a really easy thing to do, but the acceleration is hard. So that's sort of the nature of it. Before we can get all into that, though, we need a concept of work. And we, as you might suspect, it's work, and that's a word that we use in our everyday life. So if we're going to do that and use a word that we use in our everyday life, we should probably have some similarity with the actual work that we use in physics and what we know of as work. So what I like to do is I like thinking of mowing the grass. So you can take, for instance, a big rectangular yard. Maybe it's an acre. I don't know. It doesn't matter too terribly much. But let's say you have a push mower and it's got a 25-inch wide cut. Okay. If you go along the north border of a property going east and west, you could go basically one whole track along the north edge and then turn around the lawnmower. And now you've cut a 25-inch by whatever the northern end of the property is in length, like say 120 feet. Now we've got a 120 foot by 2 foot 1 inch cut. And then we turn it around, we can make another 25-inch swath cut out. And if we keep doing that, then we'll just have a series of cuts, and the work done would certainly be proportional to the number of times we walk north or east and west are parallel to the north line. So in that sense, you can start thinking that work is in some sense directly related to the distance of travel. So if you're thinking of an acre and you say an acre is going to be 120 feet by, actually, I can tell you exactly what it is because I happen to be the nerd that knows what an acre is in square feet. So if I did 43,560 divided by 120, because 43,560 is the number of square feet in an acre, that would be 363 feet. So we might have one border that's 363 feet and the other border that's 120 feet long and it's perfectly rectangular. So we could walk 363 feet with the mower and then turn around, line my lawnmower tires up with the first set of tires, but only one set overlapping. So then I cut a new swath, and now I've got, instead of 25 inches after cutting two swaths, I now have 50 inches. And then I turn around and cut a third swath. Now it's 75 inches wide. But in each case, it's, 25 inches by 363 feet. and then 25 inches by 363, and then 25 inches by 363. So at the end of all that, you could basically divide the 120 feet by 25 inches, and that would tell you how many paths you have to go east and west. So in some way, when you're doing an acre, you can see that the amount of work is directly proportional to the distance traveled. And in fact, if I did 120 times 12, that would be the number of inches, and I divided that by 25, then I'd find that it takes me 57.6 swaths east to west for me to cut an acre. So it would be reasonable to say that work is directly proportional to distance, in which case an acre lot would be 57.6 times 363 feet. If I did 2 acres, then that would probably be twice 57.6 and then times 363 feet. So we'd reach the conclusion that work is directly proportional to the distance traveled. Now, if you consider instead of a 1 acre lot and a 2 acre lot, let's consider just a 1 acre lot. But in one case, we're going to cut it with a 25-inch lawnmower that weighs 50 pounds. And then the other case, we're going to cut it with a 25-inch lawnmower that weighs 100 pounds. I think you would all conclude that the cutting it with a 100-pound lawnmower would take more work than cutting it with a 50-pound lawnmower. Does that make sense? So when you think about it that way, then you say, okay, well, wait, maybe work is also proportional to the force you actually have to apply. And you're getting close. In fact, work is directly proportional to force, and it's directly proportional to distance traveled. The only thing is, it turns out that whenever you apply a force to something to make it move, there's often a component of the force that has nothing to do with it moving. So for instance, if I'm pushing a shopping cart or a lawnmower, my arms might be pushing down at a diagonal. So the force is along that diagonal, which means it has a negative y component and a positive x component. That x component is actually parallel to the motion. So that one's helpful, but that other one's just wasting. So if you think about it that way, then you can say, okay, well, maybe we should define the work to be proportional to the force component parallel to the distance. And then you're actually getting closer to the formula. In fact, the way they do that is they say you take the force and you do a dot product with it. That's a new mathematical operation that hopefully you already know about. But by taking a dot product with it, you get F times D times the cosine of the angle between the D vector, which is a vector pointing from the beginning of the work path to the end of the work path. So it's just a displacement vector. And the force is another vector, and that, of course, is parallel to the motion. But if you take F times cosine theta, since it's D times F times cosine theta, then the F cosine theta gives you the component of F that's actually parallel to D. So in some sense, the work is going to be F times D times the cosine of theta. But to be honest with you, you might run into a little segment of a yard where you have to do quite a bit of work because the force is changing really rapidly in that area. Maybe there's a pothole, maybe there's a ditch. Who knows? All sorts of stuff could happen. Maybe it's soft ground, maybe it's high grass. But the main thing is now you're looking at a force that could actually change along your path. If that's the case, then what you want to do is take that whole long path that D vector represents and cut it up into little slivers. Those little slivers are going to be as small as they need to be so that the force is basically a constant over that little part of the path. If you find that the force changes a bit from one part of the path to the other end of the to the other part of the path, then you've made the division of the path too big. Make it smaller again. Now is the force constant all in that one little part? If it is, then yeah, you're happy. Okay. So how do we do that? How do we work all that out? Well, that turns out to be a neat little formula. So I'm going to give that to you. Let's go ahead and share my screen with you guys. So as soon as that comes visible, I'll write down some stuff that'll make some sense, hopefully. So what we found initially was that work is directly proportional to force, and that work is directly proportional to distance. But we also found that work should probably be proportional to F parallel D. And this means the component of F that is parallel to the displacement D. Okay. So that makes us think that we're going to do work is proportional to F times D times cosine theta, where you can sort of represent the force as like this vector, and then you can represent the displacement like this vector, and then when they're tail to tail, that angle equals theta. Okay, so that's actually how the theta is defined in terms of this work formula. Now, if you imagine breaking that F up into a component that is perpendicular to the actual displacement vector, and then there's another component that's actually parallel to the displacement vector, what you'd see is this is F parallel and this is F perpendicular. So you see, in fact, that F parallel is the same thing as F times the cosine of theta. So that's where the dot product comes into play, because it automatically takes that cosine theta. Now, if you're dealing with a displacement that's not represented by a straight line very well, then you've got to divide it up more. So you might have a path, something like this, and you're going this way and this way and this way. You can see, for instance, when we're right here, we'd have to break it up very small to make each little path essentially straight. But then right here, we can go maybe as far as that, and then we have to do small spaces again. And then we can do a long one, and then we can do small ones again, like that. So that's how we could actually break it up. But when we break it up like that, then you're going to have a bunch of different parts. You're going to have a part for each one of those little segments of the path. So how do you end up doing it? Well, the ultimate formula is work is equal to the integral of F dot dl, and this is called a path integral. So this is a new type of math that you can find, for instance, in your calc book. It would be towards the end of it, but to be honest with you, I've never known of a Calc 3 class at Chapel Hill, at NC State, at Duke, at Carolina, or excuse me, I did say, I thought I said Carolina, but I might have, and not at East Carolina, and not at UVA, and not at Virginia Tech, from what I've heard. I haven't had any of those courses, or nor have I heard any of those courses ever reaching the part of the calculus textbook that gets into surface integrals and line integrals and stuff like that. But in principle, you could. Maybe if they were at Princeton or Harvard or something, maybe they do that, or maybe they might be one of those cases where they don't even cover that because they expect everybody that went to Princeton or Harvard, they've already had calculus. But I don't know. The main thing is it's often not covered because you just can't cover that much material in that much time. So we're left here with the physics part teaching it to you. So the nature of this that makes it different is specifically you've got to take the integrand of a path or line integral, and you've got to make it correspond to being on that path. So for instance, if you were let's say you're going from the point x equals 0 to x equals 2. So if I did something like that, we could imagine here's a y-axis this way. Here's the x-axis this way. Let's say this is 1 and this is 2. And let's say you're starting right here. So this is your initial position A. And then you're going to go to some other position. 1, 2, 3, 4 right here. And it turns out that you're going to go through this spot as well. So that could be your path. Your path could just be that solid line from the origin to the point 2, 4. So we know that equation specifically. That equation is y equals x squared. So for instance, if you had something like f is equal to 3y x cubed I hat plus 7 x squared over y j hat, if that was your force, then what you could do to actually make it a path integral is you could go in and replace the y with x squared. So now I will say f on path is equal to 3 times x squared x cubed I hat plus 7 x squared over x squared j hat. See how I did that? That's a typical thing you would do to tie the integrand to a specific path. So if you make the substitution y equals x squared, that would always keep you on the path. The other thing you have to do is you could choose DL to point in the direction you're going. So it turns out this goes either in a positive coordinate direction or the direction. In other words, I went from the origin to the 0.24. That's the actual direction of travel. So I could make, since I'm going in the x direction now that I've gotten rid of all the y's, I could call DL, I could call that DX I hat. And the fact that it's positive says it's going in the increasing x direction, and that's fine. I could leave it that way, or I could say, wait a second, I want to use this DL to point the direction I'm actually going. And then I would have to make sure that I point it in the positive x direction. But that's the same in both cases. The big deal is you either use the DL to show which direction you're going, or you use the limits of integration to show which direction you're going. Otherwise, those things point in the positive coordinate direction. So for instance, if I wanted DL to, or if I wanted the direction of my integral to be specified by the range of integration, I would say integrate from x equals 0 to x equals 2. And then I'd make DL point in the positive I hat direction because that's a positive coordinate direction. Now, just to make sure you understand that there's really no way of getting this one wrong. If I instead decided to indicate my direction with the DL, I would call that positive DX I hat. And then I would let my range of integration or my limits of integration go from x equals 0 to x equal 2. See, it's the exact same direction in both cases. So the main thing is one of them has to specifically correspond to the direction you're going, and the other one has to be in the positive coordinate direction. So limits of integration go in positive chord or in direction of integration. So like in this case, obviously I'm going left to right. So in both cases, it would be dx I hat positive, and it would be from x equals 0 to x equals 2. Okay. So we'll have more chance to do that, but this is the general part of it. Now, the additional thing that we're showing here is a new quantity called the dot product. So there's a dot product that I've introduced here, which again, I suspect y'all have had this to some extent in pre-calculus / trig, but here is one of the many formulas. A dot B could actually be written as the x component of A times the x component of B plus, notice that's a scalar quantity, the y component of A times the y component of B plus the z component of y times the z component of B. Of course, it's a little different if you're using other coordinates, but this is specifically a way of calculating the dot product. You multiply like components, and then you add those results and you get a scalar quantity, because the dot product is also called the scalar product. Okay. Now, another way that you can specify the dot product is you can take the magnitude of A, which we can write as just A. You could also write it, of course, A with a vector symbol over it with absolute value bars on it. That would be acceptable too. But we write it as AB times cosine theta, again, where this is vector A, this is vector B, and when they're tail to tail, that's our angle theta. Okay. So that's the two ways you can calculate a dot product. So if you can get your dot product, or if you can get your vectors into IJK notation, then you'll have their x components, y components, and z components. And then you could use the ax bx plus ay by plus az bz method. When you do that, you actually would get an answer for the dot product. Now you could take the vector A and find its magnitude, and then you could take the vector B and find its magnitude, and you'd put them right in here, because you know all this, and now you could know that, and that will actually be the way that you could use to find out what the angle between those two vectors are. You can say A dot B is equal to 47, for instance, and then A times B might equal 72. And then cosine theta would be 47 over 72. You take the inverse cosine of both sides, and that would give you the actual angle between the vectors. So that's the beauty of the dot product. And you can tell by looking at it again, I'm going to use the same stuff I did before. I can break the A up into a component that's perpendicular to B and a component that's parallel to B. This would be A cosine theta, and this would be A sine theta, which is A perpendicular. In other words, that's the component of A that's perpendicular to B. And this is the component of A that's parallel to B. Now, you could also draw this and realize that B times cosine theta would be the component of B parallel to A. So that works as well. So all of this points us to some understanding of what the actual work is in a more general sense. Okay. So we can do that, but let's start off with the smaller stuff. So for instance, I'm going to take, this is example 7.1. So in example 7.1, what we're going to have is a crate. And I'm saying it's example 7.1. I could make it a little different, and I'm going to, but that's mainly because, I don't want to put up copyrighted material up here. But what we're going to do is we're going to say a box has a mass of 100 kilograms, and it lies on a level floor like that. Okay. And I'm going to pull on it with a force F, and that force is going to be equal to FP. We'll have a force of 200.0 newtons, and specifically, that is at a 37-degree angle. Okay. That's at a 37-degree angle with the horizon. We also have a friction force. And this friction force is actually going to be equal to, let's make this one 70.0 newtons. And we're also going to have some other forces on it. What I'm going to do, though, is we're going to actually make a displacement vector. And that distance for that displacement vector is, in fact, 80.0 meters. Okay, so that's our displacement vector that I drew there, and the magnitude is just d, which is 80. Okay, now if I draw a free body diagram, what I do is make an x and y axis like this. This would be my y axis. This would be my x axis. I have a mass, which is 100 kilograms. Now I have acting on that mass, I have a positive force acting upward. That's what we call our normal force, Fn. And then I have a negative force acting downward, and that is mg, which is obviously 100 times 9.8. That's 980 newtons. Okay. Now I also have acting on it a force that's not along any coordinate. So I'm going to draw that as blue and call this angle right here 37 degrees. Now, what that gets me is the ability to draw a x component, which points in the positive direction, and a y component, which also points in the positive direction. So this would be FP. That blue vector there is the force FP. So this one in the y direction is FP times the sine of 37 degrees. And this one down here is FP times the cosine of 37 degrees. And then we also have a friction force that is acting this way, and that is 70.0 newtons as the friction force. Okay. Now, we didn't necessarily have to do that full free body diagram, but I wanted to make sure you understood all the forces acting. And we can go ahead and take the FP, since that's supposed to be 200 newtons. I can say 200 times the sine of 37, and that gives me 120 . That gives me 120.36 newtons in the positive direction. And for this one, this is going to be 200.0 newtons times the cosine of 37 degrees. So if I do 200 times cosine 37, that one gives me 159.73. newtons, and that's also in the positive direction. Okay, so now we've got all our components, we've got all our forces pointing in the different directions. to be honest with you, really all that matters, though, in this case, they're asking the floor is rough and exerts a friction force of 70.0 newtons. They want me to determine A, the work done by each force. What is the work done by each force? And then B, they want to know the net work done on the crate. So when they say net, they just mean add all those up. That makes sense? Okay, so now I'm going to work for my solution. So this is the solution, and I'm first going to do part A. Let's do the work done by friction. That's equal to the integral of f dot dl in general, right? But what we see here is the force is a constant, so it's really just going to be F times D, but it will be times the cosine of the angle between them. So the force is going to be 70.0 newtons. Now that vector is pointing in the negative x direction, and the D vector is pointing in the positive x. So that means the angle between them is 180 degrees. So I'm going to say 70.0 newtons times 80.0 meters. And then I'm going to say times the cosine of 180 degrees. Does everybody understand why we're using 180 degrees? So remember that the vectors are supposed to be tail to tail. And when they're tail to tail, D points to the right, F points to the left. So clearly that's 180. Now, if I multiply that, I'll say 70 times 80 times the cosine 180. And that's going to give me negative 5,600. And what we get is a Newton times a meter, which is defined to be a joule. So 1 Newton times a meter is defined to be 1 joule. That's Joule. I'll tell you that a joule is about as much energy as it takes to lift a good, fresh, red, delicious apple from the ground to the top of a kitchen table. So that's a typical amount of work. So basically, that friction's doing enough work where it's basically lifting 5,600 red, delicious apples to the height of a table. So there's the work done by friction. I'm going to go ahead and box that off. So we'll recognize it as an answer.
So if you use 180 degrees, how come it's cosine instead of like sine or something, since it's just a straight line?
Well, in this case, they were actually in opposite directions. You would have just did cosine of 0 if they were parallel. So the formula for the dot product is specifically made with the cosine in it because it's supposed to take the component that is parallel to the other vector.
Okay, so it's because the FP component is the same direction or the opposite direction. That's why you're using the cosine.
Yeah. If you wanted, for instance, to take the work done by the Fn, then that's going to be the cosine of 90 degrees, which is going to give you 0. Does that help you make more sense of it now?
Okay, I got you.
Yeah, because we only want to count the parts that are actually contributing, and any parts that are making it harder, they're ultimately going to make it a negative amount of work. So the friction's actually making it harder for us to pull it across the floor. Therefore, it's doing a negative amount of work. Another way of looking at it is a negative amount of work means that force is losing. That force is applying a force, but despite that force, the object's going the opposite way. So that's another way of thinking about the negative work. Does that make sense?
Yeah.
Okay. Now, if we want the work done by that was the friction force. If we want the work done by the normal force, we could say the work done by F normal is equal to F normal, which you can see from the summation forces in the y direction equals mass times acceleration in the y direction, which is 0. That tells us Fn minus 980.0 newtons is equal to 0, and that means Fn is equal to 980.0 newtons. So we can go ahead and do this as well. That's a constant force again. So we're just going to get a constant force times d cosine theta. So in this case, it's going to be 900. Oops, I should probably write in purple. It's going to be 980.0 newtons times 80.0 meters. And this time times cosine 90 degrees. Okay. Now, the reason why we're not doing an integral here is because the force nor the direction of the between the force and the d vector changes. If the force magnitude or the force direction changed anywhere along that path so that the cosine angle would change, then yeah, we'd have to actually do the integral part, but we don't have to do that for these. So in this case, I'm going to get just plain 0.0 joules because the cosine of 90 degrees is 0. So that's the work done by the normal force. Similarly, the work done by gravity or by the weight is equal to 980.0 newtons times 80.0 meters times cosine of 90. It might even make you a little happier to say cosine of negative 90, but it really doesn't matter too terribly much. Either way, you're still going to get 0.0 joules equals the work done by mg. Now that's normal, by the way. Whenever you apply a force that's perpendicular to the direction of travel, then the work done by that is 0. Whereas if you apply a force at 180 degrees, the work done will be negative. So now we've got 3 of the forces. 1, 2, 3. All we're left now is with the work done by FP. So we'd say the work done by FP is equal to, I'm going to take the magnitude of FP, which is 200.0 newtons. It's still, again, that FP doesn't change the angle. The 37 stays the same, and it doesn't change the magnitude. The 200 newtons stays the same. So we don't have to integrate. We are going to multiply it by 80.0 meters. And then, of course, you can see the FP vector. When it's tail to tail with the d vector, it's literally at 37 degrees. So I'm going to say 200 newtons times 800 meters times the cosine of 37 degrees. That's going to bring us down to 2 sig figs. So I'm going to say 200 times 80. Whoa. Times 80 times the cosine of 37. You'll notice that 200 times cosine 37 basically gives us that 159.73. So you could actually say this is 159.73 times 80. In this case, I'm just going to take it as it is. It is, in fact, 1.278 times 10 to the 4th joules. And that's actually equal to the work done by FP. But notice if we took the 159.73 newtons, if we multiplied that by just the 80.0 meters, we would get 159.73 times 80 gives me 1.278 times 10 to the fourth joules. So you get exactly the same number. So that's the main part I'm wanting to show you here is basically breaking that vector down into two components is something you normally do when you're doing a three body diagram. But when you do the dot product in a work problem, that's actually done automatically by the dot product. So you don't have to do that. But hopefully that gives you a better understanding. Now, the next part B, they're asking for the total work done. So work net is equal to work done by the normal force plus work done by the mg plus work done by the friction force plus the work done by the FP, the force due to the person. So all in all, that gives you negative 5,600 joules in no particular order, obviously, plus 0 plus 0. So now I've taken into account the Fn and the Mg, and then I'm also going to take into account plus 1.278 times 10 to the fourth joules, and that should give me the total amount of work done. So I'll say negative 5,600 plus, and that gives me 7,178 joules. And to be honest with you, the 5,600 really gave us only 3 sig figs, so that shouldn't have been good to there. So the ones place is not good. Probably the 1.278, that was actually 3 sig figs as well. So that's not good for this place either. So it turns out that you only have 2 sig figs. You're going to have to call that 7.2 times 10 to the third joules, and that's equal to W net. Any questions on that one? All right. So notice how that works. Notice how the negatives come into play when you have a force that's actually in contradiction to the direction you're going. Then that's going to tend to make a negative amount of work. That's pretty normal. And if you have a force that's perpendicular to the direction you're going, it's very normal for that work to be 0. So those are sort of the big concepts you're learning, or you should be learning. Now let's look at something like example 7.2. It says determine the work a hiker must do on a 15.0 kilogram backpack to carry it up a hill of height h equals 10 meters as shown in the figure. Determine also B, the work done by gravity on the backpack, and C, the net work done on the backpack. For simplicity, assume the motion is smooth and at a constant velocity, i.e. the acceleration is 0. Okay. So what we have here is we can imagine a scenario where you've got basically flat ground and then you've got an incline like this, and that incline is actually 10.0 meters high. I'm going to call that H. Okay. The distance D, they did not give us, but basically what's going on here is a person's walking with a backpack and that backpack has a weight. Okay. So the mass of the backpack is 15.0 kilograms. And what we want to know is A, work done by the hiker, and B, work done by gravity, and C, the net work done. So those are the things we're trying to solve. So what we're going to do is work is equal to the integral of f dot dl, which in this case just becomes f times d times cosine theta. Okay. Now, what we can see is if we consider a free body diagram, basically this object is going to go like that. That's our displacement vector right there. Okay. And you can see it's going to be at some angle. We could call that angle, for instance, let's call this angle phi. Okay. And if that angle's phi, then what we're looking at is an angle phi. We have acting on the object a force this way. That's the force due to the hiker. We also have a force this way, and actually I should probably do that. I'm going to make that a green vector because it's pointing in the positive y direction. So that's the force due to the hiker. I'm going to say we also have a force due to gravity, which is this way. That'll be mg. And that's pretty much the only forces acting on it. Now, what you might notice is the hiker is actually walking up the incline. So he's tending to go up and to the right, but you don't actually have to have a force to do that unless it accelerates. That's why I was making the point to say that specifically, assume the motion is smooth and at a constant velocity, i.e. the acceleration is zero. If the acceleration was not zero, then the hiker would be putting a horizontal force on it as well to make it speed up or slow down. So that's what that allowed us to do by assuming it's not that way. So that's the way our forces are, and this is the way our displacement vector is d, like that. We do know that the displacement vector has a y component that is equal to 10 meters, so that's kind of helpful. But other than that, it's not that helpful. So if we are to actually do the summation of the forces in the y direction equals mass times acceleration in the y direction, in this case, we get FH minus mg is equal to 0 because the acceleration is supposed to be 0 everywhere. So in this case, we have FH is actually equal to mg. So FH is equal to 15.0 kilograms times 9.80 meters per second every second. And that gives us 147 newtons. Okay. And that's 3 sig figs. So that should be good enough. We now have that quantity. So if I want to calculate the work done, then the work done, for instance, by FH is equal to FH times D times cosine theta. Now that might, or excuse me, times cosine theta, where theta in this case would actually be the angle between FH, and D. So that's the actual theta we're talking about. Okay. Now, if you look at that on this diagram right here, you'd realize that this right here is the angle theta as well. So what you'd notice is D cosine theta is actually equal to 10.0 meters. So we're going to get 147.0 newtons times D cosine theta is just 10.0 meters. So we're going to be 1.47 times 10 to the 3 joules. That's the work done by the hiker. Anybody have any questions on that? Okay, now the work done by the weight mg, if you look at the diagram again, you'll see that this angle is the angle between F, the mg that is, and the actual D. So this might be theta prime, and I'm going to show you why I called it that, because it turns out the work done by mg is equal to the force mg, which is 150 kilograms times 9.80 meters per second every second. And then it's going to be times D cosine theta prime. Okay. Notice that theta prime is actually the angle when mg and D are tail to tail. So that's why it has to be that. What you also notice is that this is related to theta specifically by theta prime plus theta is equal to 180. Does everybody see that? Anybody have any questions on that? Theta prime plus theta is equal to 180. Because of that, we can also say that this work is equal to 147.0 newtons times D cosine 180 degrees minus theta. Okay, so in other words, if I solve this red equation for theta prime, we get theta prime is equal to 180 degrees minus theta. And that's what I did there. You can look up a trig identity, and it turns out that the cosine of 180 minus theta is the negative of the cosine of theta. So I'm now going to say this is equal to negative 147.0 newtons times D cosine theta. And again, this is just the 10.0 meters. So in this case, we get negative 1.470 times 10 to the third joules is equal to W sub mg. So that's part B, and that's part A. Now, part C, W net is equal to WMG plus WH, which equals 1.470 times 10 to the third joules plus negative 1.470 times 10 to the third joules, which equals 0. So the total work done in this case is just 0. Now, there's a reason for that, and I'm getting ready to give it to you. But first off, let me write W net. Anybody have any questions on that? Okay. So let's consider something kind of neat. We're going to say, I want to change colors real quick. Go to, let's say, I'm going to black. I'm going to separate this right here. Okay. And now something called the work energy theorem. God darn it. The work energy theorem. Now let's take and calculate the total work. So work net, often called work total, is equal the integral of the summation of all the forces dotted with dl. Okay. Now, the summation of all the forces, we know from Newton's second law, is actually equal to the integral of m times a dot dl, which might jog your memory as m times dv dt dotted with dl. Now, at this point, we could switch them a little bit and we could say equals m times dl dt dotted with dv. And what we get is the integral of m v dot dv. And of course, the integral of v dv is 1/2 v squared. So what we get is 1/2 m v squared. And we're going to evaluate that from v equals v initial to v final. So it's going to be 1/2 m v final squared minus v initial squared. And in fact, this defines what we call kinetic energy. So what we've done there is we found out that the total work done is equal to the change in kinetic energy, and kinetic energy is defined to be 1/2 mv squared. That is the work energy theorem. And this is the definition of kinetic energy. Okay, so you can tell now, since they told us there was no acceleration, that means whatever velocity it had initially, it's still going to have, which assume it'd be more or less zero. And since the total work done was zero, that would say, oh, so it didn't change kinetic energy at all. So that's why I went ahead and handled that particular part, specifically the work energy theorem right now. Anybody have any questions with that? Or on that or whatnot? Your book does another question. This is conceptual example 7.3. It says the moon revolves around the Earth in a nearly circular orbit with approximately constant tangential speed, kept there by gravitational force exerted by the Earth. Does gravity do A, positive work, B, negative work, or C, no work at all, or no work on the moon? What do you guys think? Anybody have any ideas or thoughts on that? Which way, compared to the velocity, in which direction does the gravitational force on the moon point? Anyone?
Inward?
Yeah, it points radially inward towards the center of the Earth, right? And the velocity is tangential to that circle, isn't it? So like the circle's like this in the orbit, so the velocity is tangential at each point, which means the angle between the velocity and the force is always 90 degrees. And if you look at it for just an infinitesimal amount of time, delta t, then basically the d is just the velocity times delta t. So it's the d is literally just parallel to the velocity vector at each point in some sense. So if you look at that, then you discover that the force and the displacement are at each instant 90 degrees from each other. Therefore, the total work done, or the work done by the gravitational force, must be zero. So that's a nice little example. Now, let me try to work a couple of problems regarding dot products for you. So what we can do is imagine a coordinate system. I'm going to actually try a three-dimensional coordinate system just to make it kind of neat. So let's say this is our x-axis, this is our y-axis, and this is our z-axis. Now, let's say we're going to, I want a vector that specifically points from the origin to, let's say that we go down here along the x-axis, 1, 2, 3, 4 units. And then we go over here along the y-axis, 1, 2, 3 units. So notice how I'm trying to keep those lines parallel to the other axis. And I'm going to say it has no z component. So our first vector is right here. And I'm going to call that vector A. And clearly it is 4 meters I hat plus 3 meters j hat. Does that make sense to everyone? Okay. Now, let's take another vector. I'm going to use a red vector this time. So let's say this red vector A is actually just equal to 1, 2, 3, 4, 5, 6, 7 meters I hat. Okay. That could also be written 7 meters I hat plus 0 j hat plus 0 k hat. And of course, the A vector, oops, I called that A already. Stupid. Let's call this one B. I don't know what I was thinking. Ah, darn it, wrong color. So I could also call this plus 0 k hat just to keep things straight. So does anybody know what this angle right here is from what I've given you so far? Okay, that's a 3, 4, 5 triangle. And that should be the 36.86 degrees, basically. So what I'm going to do is show you that the dot product can give us exactly what that angle is. So I'm going to start off with calculating A dot B. So A dot B, as I said, was equal to the x component of A times the x component of B, which in this case is going to be 4 meters times 7 meters plus, now I'm going to do the x component of A, which is 3 meters, times the B component or excuse me, the Y component of B, which is 0 meters, plus now I'm going to take the Z component of A, which is 0 meters, and I'm going to multiply it by the Z component of B, which is also 0 meters. So what I get is 4 times 7 is 28 meters squared plus 0 meters squared plus 0 meters squared. So I get 28 meters squared is A dot B. Now, the magnitude of A, which I can write like that, or I could just write like this, we can tell that's clearly 7 meters. The B isn't quite so easy. I can say the magnitude of B, which is also just B, that's going to be obviously 4 meters squared plus 3 meters squared square root, which gives me 5 meters. Okay. So now what I'm going to do is use the dot product to find the angle phi between A and B. Okay. So what we know is A dot B is equal to AXBX plus AYBY plus AZBZ. We also know that that's equal to A times B times cosine, in this case, phi. And I'm going to just label this phi right here. So I can now use that. I already know what AXBX plus AYBY plus AZBZ is. I know that gives me 28. Oops, I should probably keep writing in red. I know that gives me 28 square meters. And that's equal to the magnitude of A, which is 7 meters, times the magnitude of B, which is 5 meters, times the cosine of phi. Okay. So this tells me that phi is equal to the cosine inverse of 28 square meters over 35 square meters. Now, you can obviously simplify that, but I don't really care too much to. You should be able to tell it's automatically 36.86 degrees. But if I did it, I'd say shift cosine inverse parentheses 28 divided by 35, close parentheses, and that gives me 36.8. Technically, it's 87, really, so I should probably fix that, and I will. Okay, and that's exactly what we expected because it was a 3, 4, 5 triangle. Now, we can do all sorts of other neat things like that too. Let's say, what if we found the angle between the A vector that we drew in blue? And now I'm going to do something even crazier. I am going to go off from 1, 2, 3, 4, x equals 4 to x equals or y equals 4. So I'll go right here, and now I'm going to go up. And this time when I go up, that's going to allow me to make a vector that has a k component as well. So if I go actually up like this, then I can complete this line and go like that. And 1, 2, 3, 4, 5, 6, 7, 8, somewhere around there. I'm going to assume it hits right there. And let's draw this vector C, which is equal to 4 meters I hat plus 4 meters J hat plus 1, 2, 3, 4, 5, 6, 7, 8 plus 8 meters K hat. Okay. So what we'd like to find now is this weird angle between them, which is really is a weird angle, right? So let's find them. The angle between A and C. Okay, so you guys go ahead and try to work your dot product using the components of the vectors. Y'all work that. I'm going to work it too, and let's see if we get the same results. So remember A dot C A dot C should equal AXCX plus AYCY plus AZCZ. You guys work that out. I'm going to work that out, and let's see if we get the same result. Hopefully y'all got 28 meters squared as your dot product too. 16 plus 12. Okay. Now you guys compute the magnitude of A, which we already did actually. You go ahead and calculate the magnitude of C for me. And the magnitude of C, that's equal to the square root of 4 meters squared plus 4 meters squared plus 8 meters squared, which equals the square root of 96 meters squared. And that gives me roughly 9.79796 meters. Okay, so now I can figure out the angle because I know A dot C is equal to 28 square meters, but it's also equal to 5 meters times 9.79796 meters times cosine of, let's say, alpha this time, and I'm going to call this angle alpha there, so that alpha is equal to the cosine inverse of 28 square meters divided by, now I got to do 5 times that 9.79 thing, and that gives me 48.98. 9898 meters squared. So now I'm going to take the inverse cosine. I'm going to do cosine inverse parenthesis 28 divided by my previous answer. And that gives me 55.14 degrees. So now you've seen a couple of examples of how you can use your dot product, how you can calculate the dot product different ways. Notice that there is a Pythagorean theorem for 3 dimensions. Hopefully you already knew that, but just in case, I wanted to make sure I did that as well. So that's what happened when I computed the magnitude of z. Anybody have any questions on that? I actually got my A and B reversed on this magnitude up here, so y'all might want to fix that. Time's up. You guys are free to go, of course. I'll wait here to the last person gone. I know Dylan had a question. I'm going to show him that as well. But I would recommend that this goes there and this goes there. I just wrote them in the wrong place. Now, what Dylan was asking me was specifically the problem where you have basically a light beam shooting through like an elevator or something. I'm checking on it right now. Ah, here it is. Yeah, this problem says a light beam traveling horizontally enters a hole in the side of a laboratory on planet X. The laboratory is 40 meters wide. So I have a box like this. This is 40.0 meters wide. And the light beam goes in through this hole. And if the light beam hits the far wall at distance 0.20 meters below the height it entered, what is the acceleration of gravity? So what's going on here is we're imagining the light beam's going to come in and track downward that way. And what we're saying is this distance from here to here is going to be y equals 0.20 millimeters. Okay. And this one was, of course, 40 meters. So if you actually want to know what is the acceleration of gravity, that's the actual question here, then what we know is from our kinematic equations, y is equal to 1/2 at squared plus v0 yt plus y0. So what I could do is I could just basically set the change in y height to 0.20 times 10 to the negative third meters is equal to 1/2 times a times t squared. The problem is t is a bit of a problem because we don't know that. But we do know that the light was traveling at the speed of light, and we know x is equal to v0x times t. So that means t is just x over v0x. So now I can take the 0.20 times 10 to the negative third meters, and I can set that equal to 1/2 a, and then in place of t, I'm going to put 40.0 meters for the x, and I'm going to put 3.0 times 10 to the 8th meters per second for the distance, and I got to square that. Okay. So ultimately what's going to happen is A is going to be 2 times 0.20 times 10 to the negative third meters. And then I could divide it by basically 40.0 meters. That was terrible. 40.0 meters over 3.0 times 10 to the 8th meters per second squared. When I do that, I'm going to get 2 times 0.2 times 10 to the negative 3. That gives me 0.004. And now I'm going to divide that by 40 divided by 3 times 10 to the 8th in parentheses. And then I'm going to cube that, or square that, excuse me. And that gives me 2.25 times 10 to the 10th meters per second every second. Does that help you, Dylan?
I had done that, just not all together in one equation, but I must have messed up somewhere because I got 4.5, which wasn't one of my answer choices.
Gotcha. Yeah, well, that's good. That means you understood the physics well enough to solve the problem. You just obviously made some kind of careless arithmetic error or something like that, maybe. So that's good. I mean, that's good from a teaching standpoint. I feel like you understood it, so that's cool. Anybody else have any questions? All right.
Oh, I think I know what it is.
You find your boo-boo?
Um, for time, I just got X over V. I didn't get a squared.
Oh, gotcha. Yeah,
Oh, because when I replaced it, I didn't square it. So that's
that would do it.
okay. Okay.
That cool.
Yeah. Are we gonna have to know the like the shell theorem?
No, 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 no. I mean,
Okay. It
you
mentioned
do in the sense that you need to know that when you're doing a gravitational force, if it's spherically symmetric, then you can just pretend like it's a point charge, and the point is at the center of the sphere. That's all. That's what you need to know about that spherical shell thing.
okay, because there was like some examples where it started getting into what it actually is, and it was super confusing.
Yeah,
And
yeah,
I
that's
tried to
not an
watch
easy
videos on it.
problem.
The videos didn't clarify it. They just were just going into the numbers of it. And I was like, yeah, I get that, but like, what is it? And none of them were explaining actually what it was.
Yeah, to give you some idea, Newton was the one that was able to do that. So it's not necessarily that trivial. You can, in principle, do it, but no, you don't need to know that spherical shell thing. It's just basically he was able to show us that we can pretend spherical distributions of mass are just like point charges at their center.
Okay.
All right.
All right.
Anything else I can help you with, sir?
No, I think that's it.
All right. Well, have a good one, Dylan.
You too.
Keep an eye out for the practice tests. They should be coming soon. And have a good one.
All right. You too.
Later. Bye bye, everyone. Bye bye.